Hello. Today I wanted to take some time to talk about rotational dynamics. We've already talked about rotational kinematics, and really what it comes down to is just replacing variables. We have our traditional variables of x for distance, v for velocity, and a for acceleration, and then t for time. And when it comes to rotational kinematics, we just replace them with rotational quantities. So our x becomes theta, our v becomes omega, our a becomes alpha, and our time t stays the same. Today we're going to continue this, and we're going to add in two more variables, mass and force. So we've already talked about it briefly. Our mass becomes what we call our moment of inertia, which is really equal to mass times radius squared, or some version of mass times radius squared. And our force becomes torque. Hopefully you guys remember talking about torque last year, in which it's just equal to force times lever arm, or length. So when we're using these, we can use our same old kinematic equations like x equals 1/2 at squared, and we just replace it with our our rotational quantities. So it becomes theta equals 1/2 alpha t squared instead. And we can do this with a variety of our formulas. Vf squared equals v naught squared plus 2ax simply becomes omega f squared equals omega naught squared plus 2 alpha theta. And so we're just replacing our linear variables with our rotational variables. And we also talked briefly about kinetic energy, which becomes 1/2, or is 1/2 v squared, mv squared. When we're talking about rotation, it becomes a rotational kinetic energy, so we use subscript r, and it equals 1/2 I omega squared. So we replace our mass with our moment of inertia and our velocity with omega. And then what we're going to talk about today is one more formula, F equals ma. We can say the sum of our forces equals mass times acceleration. And we do the same thing. We replace our linear variables with rotational variables. So this becomes the sum of our torques equals our moment of inertia times our angular acceleration. So what this tells us is just like how a linear force creates a linear or tangential acceleration, a rotational force, known as a torque, will create a rotational angular acceleration. And so just like before, this torque equals force times lever arm, which then equals moment of inertia times alpha. So before we talk about torques, let's talk about our moments of inertia. So our moment of inertia is basically the resistance of an object to rotate in a circle. Just like how an object resists forward, backward motion, an object resists rotation as well. And so our moment of inertia is that natural resistance to rotate. And we can calculate it, I, as just the sum of mr squared. So what this means is it's the sum of the mass times the radius squared of all of our individual pieces. So let's look at an example. If we have an object, let's say this is our point of rotation. So that means this is the point where everything is rotating around. And then we have an object that's right here. And this object is a distance r from the point of rotation, and it has a mass m. And so it's going to rotate in a circle like that. So the moment of inertia of this system is just going to be the mass times the radius squared. So the distance it is from the point of rotation. Now if we add more objects to this system, let's say we add a second object there, and then a third object there. Then it simply becomes, we'll call this m2, we'll call this M3. And let's say that object 2 is a distance R2 from our point of rotation, and object 3 is a distance R3 from our point of rotation. Then our formula just becomes M1 R1 squared plus M2 R2 squared plus M3 R3 squared. So we just add up all the pieces to get our final total moment of inertia. And it's the sum of all of our pieces. However, if we have an object that is very oddly shaped, so let's say we have our point of rotation right there, and our object is very weirdly shaped like that, we can no longer just simply use I equals the sum of mr squared. And instead, we have to advance to more sophisticated means and turn to integrals. And in that case, we can say I equals the integral of r squared dm. And remember, r is still this distance, radius, of the rotation. So let's look at a more complicated example of how to find the moment of inertia of an oddly shaped object. Okay, so here we have one of your Quest homework assignments, or one of your Quest problems rather, on your homework assignment, and it basically gives us this right triangle on a coordinate system. In the first part, it asks to calculate the center of mass of the triangle. Since we've already gone through several examples like this, I'm not going to go through the first part. Instead, I'm going to skip straight to the second part of the question where it says, if the mass of the object is 1 kilogram, find the moment of inertia of the triangle with the y-axis as the axis of rotation. So meaning this triangle is going to spin around the y-axis right here. So, because this is not a uniform object, we have to use an integral of I equals the integral of r squared dm. But our r, or radius in this case, is this distance right here. And so instead of using r, I'm actually going to use x squared dm because it goes along our x-axis. So the process of solving for this moment of inertia is very similar to the process that we use to solve for the center of mass. The first thing we want to do is we want to substitute for our dm. We want to put our dm in terms of x. And the way we can do that is by defining the mass of the triangle. And so if we break this triangle up into a whole bunch of small rectangles and define the mass of each rectangle. The mass of each rectangle is going to equal its height y times the density times the thickness times the width x. And so this gives us an expression for the mass of one of these rectangles. But we're going to make these rectangles infinitely small. And so as they get skinnier and skinnier, our term x changes, so we'll say dx, and in return, our mass, dm, is going to change. So this tells us our change in mass will equal y times density times thickness times our change in width. So we can go ahead and substitute this in for dm. And it'll give us I equals the integral of x squared y rho t dx. So from here, we can see that rho and t are constants. They're not changing, so we can move them outside of the integral. So this will give us yt times the integral of x squared y dx. And so we can worry about rho and t later on. We can deal with them at the very end. But now, let's focus on what's inside the integral. X squared is fine, but y, we can't have y. Y is not a constant. It is changing, but it needs to be in terms of x, because our integral is in terms of x. So, if we look at our diagram, just like we did with center of mass, we can look at this line. And we can come up with an expression for that line in terms of x. So we can say y equals mx plus b, where m is our slope, which in this case, for this triangle, will equal rise over run. So it's -4/8, or -1/2. And then our b is our y-intercept, which we can clearly see is 4. So this expression becomes -1/2 x plus 4. So let's go ahead and plug that in for our y. So that gives us an expression of I equals rho t times the integral of x squared -1/2 x plus 4 dx. So now everything is in terms of x inside the integral, and we can just distribute a little bit and then we can solve. So this becomes -1/2 x cubed plus 4x squared dx. So now we need to put limits on our integral so we can go ahead and solve. And since our integral is in terms of x, our limits need to be in terms of x as well. And since our triangle goes from 0 to 8, our limits will be from 0 to 8. And so then we can go ahead and solve the integral. Hopefully by now, solving these types of integrals is not too much of a challenge, so I'm actually not going to go through all the steps of it. And instead, I'm just going to jump to the answer, which gives us rho t 170.66. And the 6 repeats on forever and ever. So, clearly this isn't our final answer because we still have rho and t in our answer. So now let's go ahead and deal with those two variables. And so we can get rid of them by defining density, which is mass divided by volume. And so in this case, since we're dealing with a triangle, the volume is 1/2 base times height. And so if we plug, times thickness, because it is a three-dimensional triangle. So if we plug in variables to this, we get the mass of 1 divided by 1/2, our base of 8, our height of 4t. And so this gives us a density of 1/16 t. And so we can see when we plug this in for our density, it gives us 170.66 over 16t. Oh, forgot the t on the top. So it gives us 170.66 t divided by 16t. Our thicknesses cancel out, and it gives us a final answer of 10.66 kilograms per meter squared, which is our final answer. So that's just one example of how to calculate the moment of inertia for a non-uniform object. So, lucky for us, people have already calculated most moments of inertia for regularly shaped objects for us. Here's just a small chart of several different moments of inertia for different shaped objects. And we can see that all these objects have different moments of inertia. But notice that they all follow the same pattern. All of our moments of inertia always have the term mr squared, or in this case ml squared. It's always mass times length squared. And then they all have a different fraction in the beginning to change the moment of inertia. So this is the basic form that all of our moments of inertia will follow. So for most problems, you'll be able to just flip to one of these charts and find the moment of inertia that you need for that situation. But notice, in this chart, we have different moments of inertia for different axes of rotation. So this top one gives an axis of rotation through the center of the cylinder. whereas this one directly below it is a vertical line through the top of the cylinder. And so depending on your moment of inertia, depending on your axis of rotation, your moment of inertia will change. So you need to be very careful in which moment of inertia you choose. So let's continue. Now let's talk about torque. And so we know torque equals moment of inertia times alpha. And just like you learned last year, torque equals force times length, which equals moment of inertia times alpha. So, just like how a tangential force creates a tangential acceleration, a rotational force will create a rotational acceleration. So, these problems, very similar to Newton's laws problems from several weeks ago. So let's go ahead and look at an example of a torque problem. So, in this example, we have a potter's wheel that's made out of thick stone of radius 0.5 meters and mass 100 kilograms, and is freely rotating at 50 revolutions per minute. The potter can stop the wheel in 6 seconds by pressing a rag against the rim and exerting a radial inward force of 70 newtons. And we want to find the effective coefficient of kinetic friction between the wheel and the rag. So basically, what we have is we have a giant disc that's rotating, and then we are applying a force to the edge of the disc that's causing friction, that's causing the disc to slow down. And we want to know that kinetic coefficient of friction. So we can start with basically Newton's second law for rotation. Torque equals I alpha. And so the first thing we want to do is we want to figure out what our moment of inertia is going to be for a solid, thick stone disc. So if you look at the chart, or any chart, online or whatever, we'll see that the moment of inertia for a thick disc of this sort is going to be 1/2 mr squared times alpha. And so we just make that substitution for our moment of inertia. We also know that our torque is going to be force times lever arm. And in this case, the lever arm is actually going to be the radius of the disc. So I'm just going to write force times radius equals 1/2 mr squared times alpha. And it's important to realize that this force is in fact our frictional force. So the frictional force times radius will equal 1/2 mr squared times alpha. So we can also break this down further to say our frictional force will equal our normal force times mu, which will, times radius, r, will equal 1/2 mr squared alpha. And so we can see our radius will cancel out and give us Fn mu equals 1/2 mr alpha, where we need to solve for a coefficient mu. So we can rearrange this pretty easily to solve for mu, and we get mr alpha divided by 2 Fn. So if we look back at our diagram real quick, this is our applied force Fa, which equals 70 newtons. And in return, we're going to get a normal force that pushes back that'll also equal 70 newtons. And so for all intents and purposes, in this example, we can say our applied force will equal our normal force. So I'm going to rewrite my equation as mr alpha over 2 Fa. So before we plug in values, the other thing we have to address is the velocity that's given. We're given an initial velocity, which I'll say is omega naught, of 50 revolutions per minute. and we can't do anything in revolutions per minute. So we have to convert to radians per second. So I can do that without too much trouble. And I'll put the minutes on the bottom. And so in 1 revolution, we have 2 pi radians. And then in 1 minute, we have 60 seconds. So if we calculate all of that, we get 5.23 radians per second. So this gives us an initial angular velocity of 5.23 radians per second. But our equation that we just discovered doesn't have velocity in it. And instead what we need is our angular velocity, or angular acceleration. So from our initial angular velocity of 5.23 radians, we also know that our final angular velocity is 0 radians per second. So we can easily find our angular acceleration as just our change in angular velocity divided by time. So our change is a negative 5.23 over a total time of 6 seconds. So we divide those and we get a negative 0.87 radians per second squared. The reason it's negative is because our wheel is in fact slowing down. So now we can plug that into our equation above and we have all the information we need to solve. So our mu will just equal the mass of the disk, which is given as 100 kilograms, the radius of the disk, which is given as 0.5. We solve for our angular acceleration, 0.87. Notice I'm going to drop the negative here because I can't come up with a negative coefficient. And so I don't want a negative coefficient, so I'm just going to drop the negative there. Divided by 2 times our applied force of 70 newtons. And so if we calculate all of this, we get a final answer of 0.31 for our coefficient. Now let's look at a second example. In this example, we have a giant pulley of unknown mass that has a rope wrapped around it, and then this block attached to the end of the rope that's falling freely, causing the pulley to spin. And as a result, the block is falling with a downward acceleration of 2.6 meters per second squared. It gives us the radius of the pulley as 0.32 meters, and we're trying to find the mass m of the pulley. So let's take a minute just to understand what's going on in this case. We have a torque that's being applied to this pulley, and the torque is equal to this tension force. And the lever arm L is equal to R, the radius of the pulley. And so all of that tension force is being caused by this block that's hanging on the end of it, that's falling downward. So, per usual, let's start with Newton's second law for rotation, which is torque equals I alpha. And so again, because our pulley is a giant, solid, uniform disk, we can substitute our moment of inertia of 1/2 mr squared times alpha, our angular acceleration. And just like before, our torque will become FL equals 1/2 mr squared alpha. But to be more specific, our force is our tension force, and our L, our lever, is actually the radius. So I'll make those substitutions, and I'll simplify our equation a little bit. Our radius will cancel out, and it'll just give us Ft equals 1/2 mr alpha. So in this case though, we don't know what alpha is. Instead, we're given a tangential acceleration. So this is the tangential acceleration of the block falling, but it also equals the tangential acceleration of a point on the outermost edge of the pulley. And so we know that our relationship between tangential acceleration, AT, and angular acceleration is alpha r. So we can rearrange this to say alpha equals AT over r. And now let's make that substitution back into our equation. And so we get Ft equals 1/2 mRAT over r, which cancels out our radiuses, ultimately leaving us with Ft equals 1/2 MAT. And so this m right here is the mass of the pulley that we're trying to solve for. So let's rearrange our equation. So it's m equals 2 Ft over AT. So we know our tangential acceleration. Now we just need to solve for our tension force. A lot of people will jump the gun and say, well, in this case, our tension force will equal mass times gravity of the block. And that would be true if our block was at rest. But our block is not at rest, so we can't make that assumption. So before we go any further, let's draw a free body diagram of the block. We know it has gravity, Fg, acting downwards, and it has tension acting upwards. So if we use Newton's second law, F equals ma, we would write this as Fg minus Ft equals ma. And I put Fg because I know Fg is larger than Ft. And then Fg becomes mg minus Ft equals ma. So from here, I can rearrange to solve for Ft, which will give me mg minus ma. And so this is my expression for Ft. And so now I'm going to go and substitute that back into there, which gives me mass equals 2 mg minus ma over AT. So I can plug into variables into this. Like such, and when I punch it all into my calculator, I get a final answer of 3.48 kilograms for the mass of the pulley. So I hope this has helped to clarify some of the rotational problems that we're going to be looking at in the very, very near future. If you have any questions, feel free to email me.